Good day, I'm Norman Walberger. Today we're going to start down the path of explicitly addressing the issues with real numbers. Real numbers can be introduced in a number of different ways that I've pointed out, and the first way that we're going to look at, starting today, is the idea of a real number or an irrational number as an infinite decimal. We already saw that an ordinary rational number, like 13/8, can be represented as a decimal number, like this, under certain conditions. When the denominator had a certain form, then we could actually divide and get a finite decimal, like in this case 1.625. And we call such rational numbers decimal numbers. And then we also had a look at repeating decimals. Something like 13/7 can be expressed as a repeating decimal where you have a period like this that gets repeated over and over again. Both of these expressions were in the context of finite expressions because, well, we can write them all down in a finite way using this over bar notation. The current understanding of decimals traces back to an interesting Flemish mathematician, Simon Steven, who lived in this period, 1548 to 1620, and he was really the first person to advocate the modern theory of real numbers as infinite decimals. Steven contributed to mathematics in a number of other ways. He investigated the tides relationship with the moon. He was an engineer and rather practical person. And he, for example, created something called a land yacht, which is a sort of a boat on wheels with sails that could go quite fast along a beach, which was quite popular back in those days. So in this work, De Tiende, which is I think Dutch for the art of tenths, written in 1585, he introduced the idea that we could possibly get away with doing arithmetic only with integers. So instead of having to deal with these difficult fractions that people at that time found difficult to work with, he said we could all do it with basically Hindu-Arabic notation. As long as we are willing to think about decimal numbers in the Hindu-Arabic form extending indefinitely. Well, we've already seen an example of that. The 13/7 repeated fraction could, if you like, be interpreted as something that goes on forever, more and more and more in that direction, just with the same pattern repeated over and over again. But Steven realized that a lot of other irrational numbers, which were popular at that time, could also be thought of in terms of the Hindu-Arabic decimal notation. So for example, root 2, you could actually calculate root 2 using the square root algorithm and get 1.414213. You could get a sequence like this, and the more you computed, the further you could go in expanding that decimal. Root 3, you can get a decimal for that, 1.732050, and again you can carry on the algorithm to proceed as far as you like. Or root 5, 2.236067, and so on. And then there ended up being other important numbers, notably pi and e, and to a lesser extent log 10, that also had very explicit formulas for them that ultimately allowed people to write down the decimal expansions of them. The familiar 3.1415926 and so on for pi, 2.718281 for e, ln of 10 or log of 10, 2.302585. So Steven said, look, all we have to do is do arithmetic with these decimals, basically in the sense of the Hindu-Arabic way of multiplying and adding, and then we can dispense with fractions. So he was a very practically minded person. He actually wanted to empower ordinary people to do arithmetic with a wider range of numbers. So now that we have these irrational numbers on the board here, it's perhaps interesting to point out that in this rather short list, we have the great majority of irrational numbers that are actually used in practice. So if you look in mathematics textbooks and you circle every time you see an irrational number, the vast majority of them will be closely related to these 6 numbers here. Maybe slight variance like 2 pi instead of pi, or root 3 on 2 instead of that one, or 1 plus root 5 on 4. But still very closely related to these ones, which is another bit of support for my claim that the amount of examples in modern mathematics is often a little bit weak. We don't have as many good examples in many situations as we perhaps ought to. All right, so what exactly is going on with these infinite decimals? Clearly there's something that has to be explained. These 3 dots, what exactly are we talking about? Well, that's a very interesting and important and ultimately contentious question. What exactly is an infinite decimal? So this is the question that we want to start to address. We need to have a very precise definition of what this object is, and this is the kind of thing that we're after. This is what it looks like. We've got a decimal point, we've got a finite number of digits to the left, we have an infinite number of digits to the right, and perhaps there is a plus or a minus sign in front. The question is, what exactly are we talking about here? And there are essentially these days 3 different answers. 3 very important different directions of going in terms of understanding what is an infinite decimal. Here are the 3 different roads that we can go down. The first, which is the most popular and the most well accepted these days, is the approach of what I call infinite choice. It's also sometimes called quasi-combinatorial. All right, so in this approach, we take the following position, that an infinite decimal like this is, first of all, a finite choice of sign. So you either choose the plus or the minus, and if you choose the plus, you don't actually have to write it down. But if you choose the minus, you have to write it down. Then you have to choose a number k. And you have to choose digits b0, b1, up to bk. And the digits are always numbers from 0 to 9. Okay, so you've chosen the sign, you've chosen k, you've chosen a certain number of digits to the left of the decimal point, and now you need to choose an infinite number of digits, a1, a2, a3, and so on, to the right of the decimal point. And these digits can each be chosen arbitrarily and independently. So you choose digit A1. Make up some number, some digit between 0 and 9, let's say 5. And then you choose A2, say 3. And then you choose A3, say 7. And then A4, maybe that's 7 as well. And you keep going. There doesn't have to be a pattern to your choices. There can be a pattern, but if there is a pattern, you can keep it to yourself. Ultimately, what's required is the infinite string of choices that you're making. And that is what an infinite decimal is. Then there's a second position. The second position we might call the algorithmic or the constructive position. It's very much like the first one, except for the crucial part of addressing the digits to the right of the decimal point. With this algorithmic or constructive point of view, we insist that the digits A1, A2, and A3 have to be determined by a finite algorithm. There has to be a finite algorithm or procedure, or you can think of a formula, you can think of a computer program, some finite way of specifying how these digits are generated. So we don't have to actually have the digits themselves all in a row. We just need this finite piece of paper that tells us how to generate the digits. That's a rather different approach to what the infinite decimal actually is. Then there's a third position, which we might call the finitist or the rational position. In this position, infinite decimals are not required, and they are deemed illogical. So this position asserts that both of these positions are unfounded mathematically, that both of these positions are problematic, and it says, in fact, guys, we do not need infinite decimals in either of these forms. Right, so I think you probably can guess which position I am going to adopt. But before I do that, we're going to have a very good look at both of these two positions. Both of the first two positions towards infinite decimals arguably involve some meta-mathematical aspects. And in my opinion, students ought to be clearly informed of the pros and cons of each of the positions. At some point in the early undergraduate years, or perhaps in the late high school years, students should be clearly instructed that there is a fork in the road here. The road of mathematics that we've all been traveling down together forks. And there are different directions to go on. And these different directions correspond exactly to these three different approaches to what is an infinite decimal. And I think students ought to be made more aware of these possibilities, and there ought to be a wider engagement of the issues, the pros and cons for each one of these alternatives. Students ought to know that this is a very important junction point. So what we're going to do is we're going to now look at the pros and cons of these three positions, starting today in this video with the first position, the infinite choice position. So let's start with the pros. There are some very significant advantages to thinking about infinite decimals in the infinite choice frame of mind. The first pro is that this approach most closely resembles the definition of a finite integer or decimal number. If you have a finite integer, well, all integers are finite, say 7,513, or a decimal number 8.7124, then to specify those numbers, ultimately what we want is to list the digits involved. So this number is expressed or specified by listing the 7, the 5, the 1, and the 3. Any other description of this number is somehow secondary. For example, I could also describe this as saying, well, this is the digits consisting of the 3 primes less than 10 in descending order, with the smallest non-zero natural number stuck in between the last 2 primes. That would be another more long-winded description of this, but it's clearly not as preferable as saying 7, 5, 1, 3. Similarly here, if this is the answer for a question on a test, I expect my students to write down 8.7124. And anything else that they write down, I probably will not accept. If you say 8.7123 plus 0.0001, well, that might indirectly represent the same number, but I'm not going to accept that as an answer. I want exactly the string of digits that appear in exactly the right order. And so the infinite choice approach to infinite decimals adopts the same point of view. It says that to specify an infinite decimal, what we need to do is we need to say what all the digits are in the right order. So this is 15.148802, and then we keep on going. Maybe there's a 6, 7, 9, and so on. So the specification of the digits is very much in keeping with what we do with finite decimals. The second advantage is that the representation is almost unique. there's pretty well only one way of specifying an infinite choice infinite decimal. So equality between infinite decimals is easy to detect. There is an important qualification, though, that we agree that something like 3.79999, where the nines keep on going, is equal to 3.80000, where the zeros keep on going. So that's the one place where infinite decimal has an ambiguous representation. There are two ways of representing it. And that's, of course, exactly when it's a finite decimal of this kind. So it's exactly the finite decimals sitting inside the infinite decimals which have these ambiguous aspects to it. But otherwise, the representation is unique. And now we come to what's perhaps the most important advantage in this infinite choice approach. The advantage is that this idea or concept turns a process into a number. Let me try to explain what I mean by that. So in certain situations, we have problems which we cannot exactly solve, but we can move towards a solution. And we've seen that with regard to Newton's method. So for example, suppose we have this cubic equation represented by that graph, and suppose that we're interested in finding its zero. Say that the biggest zero, that one that's right there. So if you look back a few videos into my videos that have Newton's method in their title, you'll see that we've outlined a rather explicit procedure that allows us to generate rational approximations to a number that satisfies this equation. We may not, in fact, ever be able to get a number that exactly satisfies this equation, but we can generate numbers step by step that more and more closely solve this equation. Geometrically, we may start with a value x, say r1, and then using Newton's method, we generate r2, and then r3, and we can keep going, generating more and more rational numbers that are getting closer and closer to having the property that they're both on the x-axis and on this curve. So we get successive approximations, r1, r2, r3, and so on, all rational. So when we convert these numbers into decimal form, giving us repeating decimals, then we notice that the initial strings of these decimals start agreeing. The difference between r1 and r2 and r3 becomes manifested further and further along in the decimal representations. So in other words, as we keep going in the process, we are essentially generating more and more digits in this infinite decimal. And what we are able to do with this idea is to turn this process into a number. The whole process of Newton's method gets encoded in the single decimal. Admittedly, it does go on forever. It has an infinite amount of information in it in some sense. And that number can then be used, according to this concept, as a number. We can do arithmetic with this number, we can see where it is, we can compare it with other numbers, and so on. Right? So a process has been turned into a number. This is an aspect of this which has the widest ramifications and seems to convey a lot of benefits. And two very important results, which are consequences of what we said on the previous page, are these two: the intermediate value theorem and the fundamental theorem of algebra. They are both results that depend on this notion of infinite choice decimal number. So it may be a little while since you've done calculus, or perhaps you haven't done calculus, so we don't need to know exactly what the intermediate value theorem says, but it's roughly that if it looks like there is a solution, then there is a solution. Okay. Somewhat more precisely, if you have a continuous function f of x with here its graph, and I won't exactly define what this means, but you can think of it as something that you can draw on a page without lifting your pen. Then if you have some points a and b on the x-axis so that the function's value at a is less than 0 and the function's value at b is bigger than 0, then there's got to be some number c in between a and b that has the property that f of c is 0. In other words, there's a 0 to the function somewhere between a and b. So this result is intimately connected with this infinite process business generating a number. So we can get at such a thing by successively bracketing. So you can imagine sort of bracketing. Instead of choosing a and b, we choose a1 and b1, which are closer, still less than 0, still bigger than 0 on both sides. And if we keep moving closer and closer and closer, we can generate this sequence of numbers. And then the idea of an infinite choice, infinite decimal, allows us to then deduce that there is actually a number that has this limiting property that we want. So the intermediate value theorem is intimately connected and dependent on this idea of an infinite decimal. The fundamental theorem of algebra, let me say it in the 18th century way, any polynomial with real coefficients, that is with coefficients which are these real numbers, can be factored into linear and quadratic factors. A remarkable and highly non-obvious theorem, which again ultimately rests on this infinite process into a number formulation that is encoded in the infinite choice approach to decimals. So those two theorems that I mentioned are just the start of a whole range of theorems in analysis, which ultimately come back to the notion of an infinite decimal. You need the notion of a real number to be able to establish these theorems as they are usually stated. Okay, we will see later on that there's often alternate ways of stating these same theorems which does not require infinite decimals. Okay, so it's not the case that these theorems absolutely require this notion, but the current approach definitely does build on infinite decimals as infinite choice creations. Another advantage of the infinite choice approach is that the truncation of an infinite decimal yields a rational number approximation. So for example, that infinite decimal that we created from the cubic equation, alpha equals 4.696392 and so on, an applied mathematician can come along and say, oh look, we're just going to chop this off and ignore all these other infinite amount of tail digits there. But to an applied mathematician, these extra digits just amount to more and more delicate information regarding very, very small changes in position. The further we go here, the more irrelevant these digits are to an applied mathematician. And I'm talking about a physicist or chemist or computer scientist here possibly also. So this is very useful that we can just take one of these abstract, theoretical, pure mathematical ideas, just truncate, ignore the tail, and we get something practical that's important, that can be used in calculations that we can actually work with. Okay. So there's a reasonably close connection between the applied maths and the pure maths point of view on the decimal level. And finally, I'm going to mention this more curious aspect to things, that a single infinite decimal number encodes generally an infinite amount of information. So this was made explicit by a well-known analyst, Emile Borel, around 1927. He created a thought experiment, really, which is now called Borel's know-it-all number sometimes. And he said, all right, what we can do is this. So list all possible questions in English. So how do we do that? Well, you can, if you're given a question in English, and let's say that it's a question that has a yes or no answer. So you write down a question in English that has a yes or no answer. For example, is 1 plus 1 equal to 2? Question mark. All right, then you count the number of letters that you used to write down that question, and then you order all the questions in the order of the size of the question. So the smallest questions first, and the longer questions further and further down our list. With questions that have the same number of letters, okay, you just order them as a dictionary would. Okay, so we have a list of all possible questions in English. And then Burrell says, all right, now define a new real number. Define it to be the number 0.A1, A2, A3, and so on, where AI, the ith digit, is either 0 or 1, depending whether the answer to the ith question is either no or yes. So it's going to be a decimal number that only has zeros and ones as its digits. And if you want to know the answer to the ith question, you just go to the ith digit and have a look to see whether it's 0 or 1. Well, in fact, Burrell's attitude toward real numbers is rather interesting because it changed rather dramatically during his career. He was initially rather a firm advocate of real numbers in this sort of infinite sense. But as he got older, he changed his mind and became more and more skeptical about whether this really made sense. And this number that he defined was really an attempt on his part to suggest that this whole thing doesn't really work, because this is so obviously silly. Okay? You know, one can talk about such a number, but it's really sort of like at the level of philosophy, not mathematics. Right? So, although there are still people today who look at this and say, oh, isn't that interesting? You know, we have a single real number that contains all possible information, or something like that. But Burrell's approach was that this really shows that there's something fishy about this idea of having an infinite amount of information contained in one single number. So that's been a list of advantages in thinking about a real number as an infinite decimal involving an infinite number of choices of all the digits, one at a time. However, there are some strong disadvantages to this approach. So let's have a look at the cons now. The first con is that it is actually impossible to explicitly exhibit such an infinite decimal. You cannot actually write down such an infinite decimal and show it to us so that we can all see it. For example, here's an infinite decimal. 3891, so 3,891.200405624113. And this is part of a tape. This is an infinite tape that goes infinitely in that direction. And someone has gone through here and chosen each one of these digits. And we don't know what they had in mind. Maybe they were flipping a coin. Maybe they had some pattern in the back of their minds. Maybe they were just thinking of the next number that came into their minds. We don't know, but there's some sequence of digits that goes on and on forever in this direction. And when we say on and on forever, well, this clearly is a meta-mathematical thing. It's not something that we can actually demonstrate in our universe. There are no infinite tapes. There are no tapes that go on, past the end of time. It's impossible to actually write down such a number in its entirety. So it means that mathematics now is at a different level than it was before. We are no longer just restricting our attention to objects that can be written down explicitly, to computations that we can hand to someone else and say, have a look, check this. We are now at some kind of thought experiment level, where we're entertaining these notions which are in some sense metaphysical. The point is, you cannot actually exhibit explicitly such an infinite decimal. Second point, it is impossible to define the operations of addition and multiplication on such infinite decimals. And we won't even speak of subtraction and division. So, why is that? Why can't we perform these operations? Well, we saw already when we were talking about repeating decimals or rational numbers that defining addition and multiplication was already a rather delicate topic for repeating decimals. So we indicated roughly how that would go, but we didn't actually do it precisely because it involved these carries and having to keep track of how the carries from the right affect things as we go on. Well, here with these infinite decimals, which are not necessarily repeating, for which there's not necessarily any pattern to them, the problem becomes even more and more difficult. Let's illustrate it. How are we going to add this one and this one? And by the way, this one is the same as this one. I've just pulled the tape over a little bit to show you a little bit more of that infinite decimal. But you have to remember, this thing goes on infinitely in that direction, supposedly. And here's another one also going on infinitely in that direction. And there's no necessary rhyme or reason to these digits. They just are. Okay, so how do we propose to add these two things? The problem is we have to specify an algorithm for doing this. I claim such an algorithm is not possible. Let's have a look. Let's try to do it here. And we'll try to do what pretty well the only thing we can. We're going to adopt the Hindu-Arabic approach. We're going to proceed left to right because we can't start on the right. But we will be conscious of the fact that carries will be coming in from the right that we're going to have to use to modify things that we've already written down. So here there's no thousands. Here there's 3,000, so we'd want to write a 3. But then we look at the next one and we see, oh, that's going to be 8 and 7. That's going to be 15 with a carry of 1. So I'm going to put a 4 here, not a 3. Okay, I'd like to write 5 here, but I should check the next digit first. Okay, so maybe temporarily think of a 5. But the next digit is a 9. Okay, so that 9 there means that I better go one more digit to see what happens. The next digit is also a 9. Okay, so I need to go one more to see what happens. The next digit is an 8. Okay, that 8 there means that there's going to be no carry to that 9. That really will be a 9. That really will be a 9. And that really will be a 5. Good. Okay, so this 2 plus 6 was an 8. And is there a carry at the next level? No, there isn't, because that's going to be something like 1. So there's an 8 there. And then there's a 1. Not going to be any carry. I have to keep looking to the next term on the right to see if there's a carry. 0, 3, that's 4. And then there's going to be, oh, here's a 9. 4 plus 5 is 9. The next one is 0 plus 9. It's another 9. The next one is an 11. Okay, so that 11 makes a carry to that 9, making it a 10, making that 9 a 10, making that 3 a 4. Okay, the 5 and 6 was an 11, that was a 1. And then there's a 7 next, so there's a 1 there, and then there's a 7, because the next one is 4. And then the next one is 4. Well, but wait a minute, that 4 there, 4 plus 0, is followed by a 1 plus 8, which is 9. And the next one is 3 plus 6, which is also 9. And then 7 plus 2, that's also 9. 0 plus 9, that's also 9. 8 plus 1, another 9. 4 plus 5, that's another 9. 2 plus 7, that's another 9. I'm sorry, I'm stuck right here at this point right here because I have followed it a bunch of 9s. I need to know what the next one is to determine whether these 9s are going to cascade and turn that thing which is currently a 4 into a 5, or whether the next one is going to be something less than 9, in which case there will be a whole bunch of 9s here and a 4. So I'm forced to move the tape over. I need more information about the tape to be able to determine that digit in the sum. And here's where the problem is. All right, the problem is I can move the tape over, but this perverse pattern of these things adding up to 9 can persist. I could move this over 10 feet, and it might be that all of these digits adding up to 9 keeps on going. Get a total of 9, 9, 9, 9, 9, 9, 9. I'm starting to think there's some kind of conspiracy. The person who gave this number and the person who gave this number, they conspired to make this job difficult for me by arranging that their totals are going to be 9s. So how am I going to solve this problem? How am I going to say precisely how to find that digit? Well, I can't say look for the next 3 miles, because the next 3 miles might not be enough. I may have to move this thing over 100 light years before this sequence of corresponding 9s actually finishes and changes. But here's the painful possibility. It's possible that the two people who were responsible in creating these infinite decimals, they each had independent choices. They could have been conspiring so that this pattern of numbers adding up to 9s goes on forever. So even though we may look at one of the strings and see just sort of a random bunch of digits, nevertheless the two strings are correlated so that this pattern of adding up to 9s keeps on going to forever. And that means that I'm never in a position of finally having read the whole thing and being able to say, aha, now I know that's a 5 or a 4. You might say, well, can't I ask these guys what the pattern is? Maybe on the back of the strip of the paper there's a little footnote that tells me what's the rule that generates this pattern. But there is no such rule. That was the whole point. We said that these digits were going to be chosen arbitrarily and independently. Same with this one. So there's no way for us to predict, there's no way for us to look at the pattern or look for a pattern that can help us to decide whether these 9s are going to continue or not. So this is hopeless. We are not in a position of necessarily being able to determine that digit right there. Now you might argue, well, this is maybe technically true, but it's such an extreme case. How often, how likely is it that you're going to get such 9s occurring in the common sums? Well, actually, the fact that these things go on infinitely means that actually it will be very likely that there will be long periods of time, even if these two numbers were completely uncorrelated and these two people who created these numbers had nothing to do with each other, there will still be periods of time when they just happened, coincidentally, to create numbers whose sums added up to 9 for a whole large number of strings. And I'm talking not just about, a string of 10 or 20. I'm talking about a string of 10 or 20 light years. This will happen. It will happen almost certainly if you have two infinite strings of digits, because infinity is so much more than 20 light years. 20 light years looks like a lot to us, but compared to infinity, it's infinitesimally small. All right, so this is the kind of abstract argument that one uses when one works with these infinite things, supposedly. Okay? They're not really arguments that I believe in, because I don't believe in infinity. But I'm sort of playing along here with the standard dogma. All right, so the point is that you cannot prescribe a method to add, and multiplication is even worse, to add or multiply two infinite decimals. It does not exist. So as a necessary consequence of that, it becomes impossible to establish the laws of arithmetic with such infinite decimals. Now at this point here, I think any reasonable judge would say, let's halt the proceedings. Okay? If you've got a number system in which you cannot actually exhibit even one number, where it's impossible to add or multiply such numbers, and when you can't prove the laws of arithmetic, then you clearly do not have a number system. And it doesn't matter how supposedly attractive this might be to try to prove various theorems that you would like to have proven, still the logical structure is not there. And a judge would probably stop me and say, Norman, you do not need to go further. But let us go further anyway. There are serious other difficulties with infinite choice, infinite decimals. So one additional problem is that even our ordinary numbers that we like, such as integers and rational numbers, require an infinite presentation in this context. So what we're usually calling 19 is represented in this infinite decimal formulation as 19.0000000000. You're actually obliged to specify each one of those zeros. In other words, you still have to create an infinite tape with an infinite amount of zeros on it. Why? Because we have not allowed ourselves the possibility of having a little footnote on the tape that says, oh, by the way, at this point after here, all the entries are 0. That was not part of the definition of an infinite choice infinite decimal. In order to specify the decimal, we have to specify each one of the digits, whether we like to or not. So even our fractions and integers become these unwieldy, complicated things, instead of the nice things that they used to be. Another difficulty is that it's impossible to tell when two such infinite decimals are equal. I remind you that if you have two fractions, a over b and c over d, that they are equal precisely when AD minus BC equals 0. This is a cut and dried, concrete way of telling whether two fractions or rational numbers are the same. How do you tell whether two infinite choice infinite decimals are the same? So here's one, and here's another. Well, they certainly look to be the same up to this point, but that's only the very start of these strings. If we pull the tapes further, get a few more 100 entries, then perhaps still all the digits agree. It's easy enough to tell when they are not equal. So at the first point where they disagree, we can say immediately these two numbers are not equal. So that is possible to do. But if they do happen to be equal, how could we possibly tell that? It's an infinite amount of tape. We're not capable of looking through the infinite amount of tape in a finite amount of time and asserting that, yes, these are equal. So we've discussed some of the inconsistencies just within the framework of infinite decimals themselves. But there are lots of disadvantages that infiltrate to other branches of mathematics once you accept the idea of a real number as an infinite decimal in this way. And this is actually quite a long list that I could go through, and I've just cut it down so to keep the list manageable. All right, so one of the really key points is that the number theoretical subtleties inherent in many geometrical and analytic situations becomes lost. And so there's much to say about this. Let me just give you an idea about this. So suppose we look at the lemniscate and the folium of Descartes. And we ask, well, do these things meet and where? Of course, they do meet at 0, 0. But it looks certainly like they meet at two other points. Now, Newton's method would allow us to find some approximate rational solutions to those two curves. So using Newton's method, we can generate infinite decimals that represent these points of intersection. So the points of intersection arise, as we've seen before, as a consequence of this infinite process of Newton's method being converted into real numbers. However, there's an interesting number theoretical question here. The number theoretical question is, do these curves actually meet over the rational numbers? And that's an interesting number theoretical question. And if they don't meet, one can ask, well, what kind of extension fields, what kind of algebraic extension fields are required in order to have a larger arena in which they do meet? So there's natural number theory associated to this kind of question, which is finessed by the approach to real numbers. The approach to real numbers says we're not going to worry about fractions, we're just going to convert everything to these infinite decimals if necessary, and the number theoretical content is subsequently lost. So geometry gets actually dumbed down this way. There's a lot of geometry where there's these interesting number theoretical aspects which are hidden from the current view because of the reliance on real numbers as infinite decimals. Related to that is the issue of trigonometry, which is of course close to my heart. So trigonometry loses almost all its theoretical interest. Whenever you have a trigonometric problem these days, students are oriented to look for a decimal number answer. Get your calculator, get something to 10 decimal places, that's the answer. In fact, the real answer is not a decimal with 10 digits. Okay? The real answer is something more subtle with some number theoretical content, which of course depends on the problem. But the whole subject of trigonometry has this interesting theoretical aspect almost completely invisible to the modern mathematician. And last on my list is this sort of meta thought that creating a mathematical object by pretending that one can do something that one can't smacks of arrogance. To say, all right, well, I'm going to think about an infinite string of digits that I'm able to imagine creating. That's not something that you can actually do, but you're pretending that you can do it. So we are not gods. We do not need to pretend that we are at the level of the gods or God. We are human beings. And our mathematics should be appropriately modest and sensible. So I've presented to you the pros and cons of our first approach to infinite decimals. And it's important to realize that although there's almost no discussion about this very important issue today in the year 2012, the situation has not always been so. 100 years ago, around the turn of the 19th century, there was extensive discussion about this kind of issue and related things. So these things were hotly debated, and very prominent mathematicians opposed the idea of an infinite choice, infinite decimal. These days, there is a uniform status quo almost, with just a few exceptions of a handful of mathematicians around the world. Most people accept the infinite choice, infinite decimals approach to real numbers. And the justification that has been created to substantiate this and to overcome some of the difficulties that I've shown you is through an elaborate axiomatic framework. Mathematicians are not stupid. They realize that this theory is dubious. And so what they have done is they have created a rather elaborate axiomatic framework. And that axiomatic framework is something that one can study in set theory and logic. And its purported aim is to create a framework for mathematics. But its initial aims were very much directed towards solving the problems, overcoming the difficulties with real numbers as infinite decimals. Prominent amongst these axioms is this axiom of choice. The axiom of choice manifests itself in mathematics in many ways. But its primary role, its primary role is exactly here at the level of infinite decimals and real numbers. It essentially asserts, as a matter of faith or belief, that it is possible to choose an infinite number of digits arbitrarily and independently, and that a legitimate mathematical object results. This is a key philosophical point. Are we or are we not in a position to be able to specify a first digit, a second digit, a third digit, a fourth digit, and so on to infinity? And are we allowed to call that specification a new mathematical object, a real number? The axiom of choice says that, yes, we are. So it is a statement of belief, and its primary objective is to allow the building of this real number system. We're going to talk about axiomatics a lot more later on. I just want to alert you that the axiom of choice, though you may see it in lots of fancy versions, its real aim, right, the primary aim is very much in this direction, to try to justify this idea of infinite decimals as infinite choice objects. Next time we're going to look at that second approach to infinite decimals, which is very different to the idea of infinite choice. The idea of an infinite decimal as an algorithmic or computational object. In fact, that turns out to be much more interesting and reasonable, but it still has some serious problems. Next time we're going to have a look at that. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.